change. Fourth one is ITE performance index for set point change. And in the fifth question, fifth part, we have to find the controller which has the most conservative setting and also the one which has the least conservative setting. So basically, we have to find the KC and time constant for integral change for these
So,
four processes.
yeah, thank you, Sanjay. So the question is fairly straightforward and simple. Okay. So this is kind of an exercise to connect you with the performance index based process, what you call controller design and error synthesis based controller design. So you know the so two three things you'll keep in mind. Okay, so you have to understand that this is a sample problem that you're solving. Okay, and you may be given with a standard transfer function like first order plus time delay and can be a non-standard transfer function, maybe first order with a zero with a non-zero. You have to know how a direct synthesis method you are going to you should know how the direct synthesis method derivation, and you have to plug in those numbers and get what is the controller parameter. And ITA is fairly simple. You need to substitute the KC, tau C and all and just go to the table and figure it out. So this is a very simple transfer function. Maybe what I would suggest is don't apply for direct synthesis approach. The transfer function, in fact, the controller transfer function is directly available in the textbook. That's the way we have solved also, but don't use that. Please apply the first principle direct synthesis and come up with it and compare. That would be a good way to uh, that would be a good way to check. So the take home message from this question for you should be, given a transfer function, you should be able to compare the PID settings of different. So in this case, direct synthesis and ICA, basically performance-based controller setting. So your transfer function could be anything. So at the moment, this is a simple one so that we can solve in the class, but you should be prepared to solve any such structure. Okay, so we have and some comparison which is more conservative, which is least conservative, it's a qualitative analysis that you should also do. So it's a fairly simple problem, but my suggestion is please don't use the direct synthesis formula given in the textbook. That would be like very simple. Don't do that. But try to derive that formula on your own and try to plug in and get it. Maybe we'll come back at 120. Hemant, Ishika, Deepak, are you all with us?
Yes, sir.
Okay, try to derive and come back so that you will get that feel. But so the idea here is if you are given with a different transfer function, you should be able to do it. Okay. So 120 will maybe assemble. Will you please solve it? Thank you. Yes, Vibhav. Audible?
Yes, sir. Uh, basically, we simply need to plug in values. Uh, for first case, as it is transport involve transportation leg and first order system. From this table, we can find the value of
So
k.
just a second.
Okay, sir.
So, uh, so we are plugging in and using, but it doesn't mean that.
Sir,
Just a second.
sir, your voice is breaking, sir.
Am I audible now?
Yes, sir.
Okay, so the point that I was trying to say here is the following. So we may be plugging in and using it. So this is first of all direct synthesis. Direct synthesis, we don't have any plugging thing. So this is definitely, these are all IMC. Got it. This is not direct synthesis. So using G, so go there. G in table 12.1. It is 12.1. Okay, so it is so that's what I told. So this is whatever he has written. It can be a type. So this is IMC. So if you look at the title, it is IMC. For direct synthesis method, you will have to. You have my notes open.
Sir,
Do you have my notes open?
uh, note, sir. Okay, sir. Wait, sir.
You can just open up.
Sir, actually, I don't have notes in the PC, sir.
Okay, hold on. So I will. I'm sharing my screen. Okay.
Okay, sir.
So look at here. These all of you. Have done it before. What what it was. First order and second order system in the class. So you may get it. So in fact, yeah. So you can see it, right? So for the direct synthesis, you have to use the 12, 10, and 12, 11 equation for getting the Kc and tau I. For first order and second order, it's 12, 12, and
Sir,
yeah, perfect. It is the note. So we are in here.
sir, I guess your voice is breaking, sir. It's not properly audible, sir.
How about now? Is it audible or not audible?
Sir, it is still breaking.
Yes, sir.
Let me just come closer to the microphone. How about now?
Sir, now it's okay, sir.
Okay. So Ishik, so see whatever we have projected, right? So there is a mild typo here because that are all the results for the INC. But the question is asked for the direct synthesis. So you will have to look at these expressions for first order and second order and come up with And let's say what I told was, if it is not given to you, okay, if it is not given to you, you may use whatever method that you want to get it. But see, the solutions, there is no mistake, because so now so see, Kc is 1 by k times tau by tau c plus theta, and tau I is equal to tau. And so now I will unshare, and whatever what I call Sanket was showing is correct, but the its explanation was correct. So this is not coming from the entry from that table. Go, now you share, Sanket. So see, these expressions are coming from that equation and not from the table. Your expressions are all correct. You can say they're all correct, but they're not coming from that table. But what you call it is coming from that equation. This is what I just wanted to show. And now you can, Sanket can show the results of these numbers, and you guys can verify yourself. But again, the caveat here is that this is for that particular transformation. You should be capable to derive this solution given a new and separate transfer function. Is that okay, Deepak?
Yes, sir, I derived from like the beginning and got the answer.
Yes, Sanket, now you can take over. Sorry for the interruption. Okay, thank you. Sanket, you can now take over. So all the expressions and everything is right, but the line on the top is incorrect. So it is not coming from that table. That's only my point.
Oh, okay, okay, sir. As
So
sir,
the section 10, 12, 10 and 12, 11, rest all is correct. That's fine.
so we obtain for four different cases values of Kc and tau I. Then we have to decide which one is more means conservative setting. So the case in which we get the least value of Kc is most conservative. So in second case, with value tau c equal to 1, we have least conservative setting, and in case this case we get the with Kc with highest value. So this is least conservative setting. Uh, so should I move to next question or?
So the point, so just a second, Sanket. So
Okay.
the part C and D is fairly straightforward. You have to get this case to this expression from that table and plug in appropriately. But again, one tricky business here is the following. I hope you have seen the table, but unless so, I'll again share the textbook. Yeah. So you keep it there. Absolutely. Yeah, you can share that. That's perfect. So see, this is fairly true for almost all the cases, but you see this wherever this person is P, right? So for instance, Pi and for the integral term for set point cases, for both PA and PAD, you have to use the tau I by tau I is equal to A plus B by tau expression to compute the value of tau I. So A and B you plug in, but so blindly plug in the A expression could lead to erroneous result. That is the only point that I wanted to emphasize here. Okay, so now the last point, how things become conservative. So conservative in the sense that you don't want to have any more what you call oscillatory behavior, or like it's the most tightest behavior that you could think of. So so maybe I will just share my screen a minute. So just a second. You could see this, right? So the, so the so the most conservative, what you call the value of Kc comes in when you would see that tau I value is generally Kc values are generally minimal and the tau I values are
Sir, your voice is again breaking.
so very. So how about now? So just a second. So how is that okay now?
Yes, sir.
Okay, so the point what I am trying to say is for a lower Kc and how a higher tau I value, you see that performance seems to be more safer. So you could check they are the conservative setting. You got it, no? If you look at, so this gives you an idea. The lower value of Kc, so that is the gain pressure. So the higher value of the gain, you would always see that the system is or doing sustained oscillation to come out of that, and higher value and the integral and the higher integral value also also bring in the oscillation. So one by tau I, which is basically the what we call higher. So the lower integral term means that higher value of tau I. So which means that 1 by tau I become uh, 1 by tau I is smaller, so you can have higher tau I values. That makes things more conservative in the sense that that is the most that is the area in which you can safely work. So that, so if you hear these terms, you should be able to logically say those answers. So that is the overall thing that I wanted to share. Is there any doubt on Deepak from Deepak Hemant that if he comes?
So, sir, it means that we should have a lower transfer function.
No, not lower transfer function. What do you mean by lower transfer function? There is no lower.
Since we want a small k and large I, it will simply mean large tau. It will simply means k. Sorry, the g is small.
No, how can you say G is small or large? What is the metric that help you to say G is small or large? We can only say that terms in the G, right? But like G, small G, like, so I can say 2 is a smaller number than 5. But how can you say small G is small? So there are multiple terms inside it, right?
Yes, sir.
So look at this contribution. So see, the problem here is if you have higher integral time, things tend to oscillate. How to have higher integral time? Not higher integral time, contribution from the integral. So you should have, if the tau I value is smaller, it essentially means that it would mostly result in oscillator. You don't want that. The higher value of Kc could also result in sustained oscillation. We have seen Ziegler-Nichols and K-type things. So you should move away and come to a space where you can conservative in the sense that it is the most conservative setting. So you can freely play around it. So that's the overall point. So please, so whenever these qualitative kind of reasoning questions are, please come to the table 12.1. It is shown in the textbook, and I have also placed in the note, and we also have this results in the PPID controller section. So then take a logical result. Correct. Is that making sense to you?
Yes, sir.
Okay. Okay. Thank you, Sanket. Now you can start showcasing the question number 2 and just maybe. So maybe I'll just give some opening remarks that you can explain. So this is coming from the end-to-end kind of a design. So you have been given with some step response data. Okay, so now you have been asked to do the controller design for IMC and as well as ITA. So first thing, if you look at the flow of the pipeline, the data you should be able to develop, because IMC being a model-based controller, and also ITA or the performance criteria which your Kc and tau, you have to first question that you have to take in mind is develop a model out of it. You know the step response method. Make a model, then apply IMC, ITA, and what we call based on set point and disturbance. And the next question here is again, so the IMC tabular values are given in the 12.1 stability. But again, please try to derive it from first principle, so that there is a no. If you get a non-standard transfer function, you should be able to use that. So you can directly apply for this particular case because this is possibly going to be a first order plus time delay. But let's say if you get a non-standard transfer function, what will you do? So I strongly suggest you to derive that expression and apply it rather than just using the table. Of course, we will show the result with respect to table only, but you can always reconcile. So maybe I'll just stop and Sanket can deeply explain the question, and maybe we'll wait till 1:45 or just beyond that, then we can explain the solution. Okay, over to you, Sanket. Thank you.
Okay, sir. So Process stream is heated using a cell and tube heat exchanger. The exit temperature is controlled by adjusting the steam control valve shown in figure. During an open loop experiment test, the steam pressure PS was suddenly changed from 18 to 20 psi, and the temperature data, time versus temperature data is given. At the nominal condition, the control valve and the current to pressure transducers have gained. So we have KV and KIP value. So from there we can find the value of K. Determine appropriate PID controller settings using the following approaches. First, internal model controller, in which we have to select the value of tau c. Second is ITAs for set point change, and third is ITA for disturbance changes. So basically, again, we have to calculate for PID controller value of KC, change tau I and tau d. But as compared to last one, there is no transfer function given. We have to assume transfer function based on data. So try to calculate value of 3 and first assume the transfer function.
Sir, could you upload the tutorial sheet on the Moodle? It is not there.
Sorry, actually, I'm not added in Moodle, so I'm not able to upload there. I mentioned to other TS, but probably they forget.
Sir, can we show the figure?
I think there is no need to figure, I guess. You only need to use these data.
Am I audible?
Yes,
Yes.
sir.
Okay, so yeah, so what you call, you can explain this here, so then we can take up some questions.
Okay, sir. So,
So before we start, see, it is all incremental. So the interesting part of the whole subject is this is like a ever incremental subject. So you are just nothing. Okay, there are new things, but it's all applied on the older things to make things. So there is now no joint learning that is happening in the school. So model learning and model development you have learned. Now you take up into in connection with the controller settings and controller tuning. So keep this in mind. So whatever you learned in the first chapter would be used in the last chapter. So I'm saying that's the way this overall course is, because it's fully incremental, highly incremental. Nothing new. Of course, you will learn new, but it's always applied on an existing system. So unlike, so you will learn disjoint what you call topics in different courses, but this is a very incremental thing. So even if you forget about the model building thing in the chapter, whatever, I think in the note 5 or 6, you would use it in context of an IMC. So please make sure that try to have an organic try to build an organic connection so that you'll be able to think and solve the problem. Okay, so over to you, Sanket.
yes, sir. As I said, first we need to assume, we need to model based on data. So we assume a first order and time delay kind of transfer function. As we have data of output versus time of temperature, so make a graph on that, and based on that we can get the value of theta and tau. We have values of KIP and KV, and from the data, maximum change is 16.9 to 12, and corresponding change in the pressure was 20 to 18 psi. So from there we can get the value of kV as slope intersects here, we have value of theta, and let from here we have value of tau. So based on this k, theta, and tau, we can get the values of kc, tau, and tau d from the table. So another thing is that we have to assume value of tau c. So from this ratio 1.7 to 5.5, it's around 0.3, which is greater than 0.25. So as given in notes, so we have to take value of tau c equal to tau by 2, which is 2.75. And now one can plug in values, and we can values of kc, tau, and tau d based on these tables.
So just to add, okay, am I able to do that?
Yes, sir.
Okay, so the key parameter that goes up your judgment in all of this. So basically, you have to take a judgment on taking this. So that would be tau c, because that is a closed loop type constant. Okay. So there are various ways to keep it. Okay. So see the problem. So the key problem would be, so the way is uh, so the way you would look at it, like theta by tau, you might look, and what is the, so see what is that you want to do. So the closed loop time constant, so that is something that you really would like to achieve the response. So the time constant say is the time that is required to reach 63.2%. So there are various ways. So you only need to have, so as if you look at that node, no? So there are multiple options here, option 1, 2, 3, and 4. So one of them is like what you call tau c by theta is greater than 0.8. Then another one is like tau should be greater than tau c should be greater than theta, tau c should be greater than theta, and there are many. So look at this. So unless otherwise specified, so there may be, when you solve problems, otherwise subjectivity, some clues might be given. So here I'll kind of explain the choice of this. So the rationale behind the choice of tau c is equal to half tau. See, if you see, look at the graph. So Sanjay, go to that graph. I hope you are showing. So see, what are we seeing here? So it takes around 12 whatever time units to set in, and 63% of that, so 12 to 17, so which is 5. 60% of 5 would be maybe 15. Okay, would be reaching here at the time of post 6, somewhere here. So what is the expectation? This is the natural dynamics of the system. Okay. So what is that is expected? If you add a controller to it, this response should be faster. If you really, if you don't, otherwise what is eventually it is reaching 17 after some time. No? So the performance here is looked at to make things faster. So the way conservative choice in the sense, it is just one way of choosing. Here, what are you saying? My tau c is half times the normal time constant, which essentially means that you are looking to reach the set point in half the time constant. So if it takes 6 minutes to reach 63%, you would have to reach somewhere around 2 or 3 minutes. So that is the meaning here. Okay, but here, so again, there are only given some rules. So, but like when you solve a problem for vertical, in actual settings, which essentially I'm saying in the examination setting, there would be more clues to take a more specific value. So this is what, so sometimes if you, so let's say a statement like this, okay, so you are interested to reduce the, by the controller design, you are basically interested to reduce the response time by half. So
Sir, your voice is breaking, sir. Sir, it's not properly audible, sir.
How about now?
Sir, it's better, sir. It's better now, sir.
Okay. So what I am trying to say, if you see a statement like the following, for instance, uh, you would, so by designing a controller, you would like to reduce the overall response time by half. So one way to quantify it is reducing the time constant. So here, so that is like it's like saying TC is equal to half of that. But here it is just it's just more of a conservative choice, which essentially means that you are not loading it. But my okay, so what I'm trying to say is you should be able to read the sentences like if you would like to reduce the closed loop responses by half time or something like that, and to choose a closed loop time constant wisely. Deepak, Hemant, Dishika, I hope I made my point clear. Is that so? Any confusion here? I couldn't hear you. Deepak, Hemant, Dishika.
No, sir, no problem.
Okay. So what you have to look at, of course, that option 1, 2, 3, whatever satisfied, but you have to specifically give. So let's say if you a statement like I would like to speed up the responses by 50%, 100%. So then you will have to choose the TC and tau correctly. Okay. So then go ahead, please. Yes. So rest is almost the same, but all of you are able to derive these controller settings by first principle, I suppose. Even though that 12.1 table would be helpful, but like if I give you a non-standard transfer function, they might not be able to do it very efficiently. For instance, other case it is also given to the parallel form of the PID controller. For instance, there are other options. So if you have been asked to derive something on a series form of the PID controller, so then that table is of no use to you. So make sure that you kind of able to synthesize in the generic condition. That's the take home message. Again, yeah, so go ahead. So, Sanket, please.
Sir, there were two questions only, sir. Hello, sir.
Have you done with? Okay. Maybe
Yes.
maybe I'll quickly share my screen to show some of the interesting questions in the textbook. Of course, we will not solve it though, but we will take. So let me quickly share a lot of info. Let me open first. Okay, only 4 minutes though, but I will just share some of the questions. So, so these are some other variety of problems that you would see in the textbook. Of course, we will not be able to solve all of them in the tutorials, but I think it may be a good idea. We can at least. So, of course, we can also take it in the next week because we are planning to anyway wind up the questions. So rather the topics by today. So one particular question that you would see here, you see the maybe let's move to the 12.7. So this is very interesting problem. So your GS, which is the process transfer function, is the fourth order because you see four what you call you will have to appropriately simplify this model into second order. You can approach Quajestad method or Taylor series, whatever is given to you. Then come to either first order or second order, then do it. So this is another thing that you have learned previously, which would become in handy. Okay. So another problem is of interest if you look at 11.2 here. So rather 12.2 here. Okay. So so this is a non-standard transfer function. You see, your process, as I told, 2 into 1 minus s by s. This may not be a standard transfer function that you would get it in the book. So you will have to identify what is g plus and g minus here, particularly looking at the what you call the invertible and non-invertible term and derive. Okay, this is another another problem that you would like to look into. So I would urge you to solve all of these problems and kind of get back to me at any time, maybe in the next class or maybe whenever we discuss some of these problems in the next week, so that we can discuss it further. So this is another interesting question. So what is the process as a transfer function? Okay, and you have been given the values, nominal values, tau c, and also is given like the directions by directions this approach. When you define the control transfer function, you have been given the closed loop this thing to be phi. So now this would be the question. Okay, so suppose that the controller constants are employed, but it changes from the k changes from alpha to 1 plus alpha, and you are asking what is the alpha in which the closed loop system is stable. So again, so now what are you trying to do? Now you are tying up a problem of controller design and controller stability. So we know, so when you derive the overall controller, or rather the performance driven controller design by using direct synthesis, you would say that there is an alpha coming into the picture, and this alpha would come in if you take the LCM or whatsoever. Alpha will come in both numerator and the denominator. So what you have to do, you have to take the denominator polynomial and equate to 0 and trying to find out the roots wherein the alpha lies. Alpha is positive. So how the alpha characteristics changes the overall the roots characteristic. So if it is a simpler, you'll be able to do it. But for a complex problem, it's more than to again connect back with your previously learned theory. You may have to apply root stability criteria. So if it is first order and a simple root, it's very simple. Second order maybe still simple. Again, if unfortunate circumstances you got a third order or even second order, which is not very easy to solve, you may have to apply root stability criteria to find the alpha. So maybe I'll stop here. I would strongly urge you to kind of brush through the what we call the last part of what we call the exercise programs, and we can of course discuss in detail next week sometime. Okay, Deepak, Hemant, any questions? Is that fine? Am I making sense to you?
Yes, sir, it's fine.
Okay, then guys, see you. Bye bye. Happy. Okay, of course we'll see in the tomorrow and after, but again, advanced from a tutorial perspective, advanced festival session. Bye.
Thank you, sir.
Thank you, Sanket, and thanks for participants. Bye.
Thank you. Thank you also.